in your text for today, we're looking at Fermat's theorem. We're going to be using Fermat's theorem so that we're able to knock things down, large numbers down quickly, and it's just a means of doing that. It is a pattern. It is a formula. It's something they just kind of found out, and then it just works, and then it was proved much later. In fact, Fermat was kind of famous for making ideas and not proving them and waiting for someone else to prove them. And think of how smart you'd come across if you said, oh, here's this. If you have a value to a prime minus 1, it's congruent to 1 mod prime. And people say, well, are you sure it works for everything? I said, no, I'm not sure. But no one's proved me otherwise, and it makes them look pretty smart. And dumb at the same time, because it's even smarter if you can prove what you're saying. And it was proved quite a bit later. And here's the proof right here using multiples. They took multiples of A all the way to P minus 1, and they did some multiples of the values of A, mod P, and they checked those, and they found by contradiction, P is a prime, we can cancel, so K is equal to that, which is a contradiction. This wouldn't be the case. So then they tried it with multiples, and they looked at factorials, and they found out that that is also going to cancel out as a contradiction, and so then that's how they proved it. I'm not super sure on that proof, able to follow it 100%, but you can dig in if you like. But we're going to use this A to the P minus 1 is congruent to 1 mod P in several situations. I do want you to think, though, that what if, and also, would you write, very first page, up in the corner here, I want you to write P. P is prime, obviously, but it has to be a prime. And P does not divide A. Those two things are key to making this thing work. You got to have those two. And they wrote that. P is prime, P is not divisible by A, but you got to have those two. All right. This one, turn to your neighbors and see if you can tell them how you got from A to the P minus 1 congruent to 1 mod P to this corollary. So what they were looking at is kind of what you were saying is, let's say that P does not divide A. So you can say that A to the P minus 1 is congruent to 1 mod P. And you can just multiply both sides by A. If A doesn't divide P, you can do this. Or P doesn't divide A. So this becomes A to the what? A to the P times A to the negative 1 times A to the 1 is just A to the P is congruent to A mod P. Now they did look at the situation where P does divide A. So if that's the case, you're going to have A to the P minus 1 is congruent to 0, right? Mod P. And then if you, I'm sorry. A does divide P. A is just congruent to 0. A is congruent to 0 mod P. And then what they did is they took this to the P, this to the P, and so A to the P is congruent to 0. Mod P. And then if A to the P, is related to A, you could just say A to the P. You could add A here, and it's still the same mod because A divides P. So this thing works for any integer A if A divides or it doesn't divide P. Is that okay? Kind of cool. All right, so then we get to this fun stuff. Find the value of 3 to the 152 mod 11 using Fermat's theorem. So if you go 3 to the 152, we're going to congruent that mod, what is that? 11, okay? And then you're going to check, does 11 divide 3? No, it does not. And is 3 prime, or is 11 prime? 11 is prime. So because we have these two situations, we can say that this is going to be congruent to 3 to the, remember it's p minus 1. 11 minus 1, which is 10 to the what? 15th. And you got to also have a 3 squared in there. A little bit of 3 to the 150 times 3 squared. So what are we saying that 3 to the 10th is? This is just going to be, this is going to be 1. So this is congruent to 1 to the 15th times 9 mod 11. I think this is just going to be congruent to 9 mod 11. And it is. So do you like that theorem? Pretty handy? It's pretty nice. The only thing you might have a little challenge with is this solving move. And the solving part is, let's say you have A, X is congruent to B, mod P. Okay? And what we're going to do is we're going to try to get rid of this A. Okay? What we want it to be is A to the P minus 1. Why do we want to turn this into A to the P minus 1? Then we can use Fermat's theorem. So what they essentially did is to get that, you're going to multiply everything to the A to the P minus 2. Mod P. So then A to the P minus 2 times A is going to be A to the P minus 1 times X. Isn't that clever? Times B mod P. So then this just becomes 1. And there's your formula. A to the P minus 2 times B. Remember, the mod has to have a prime for the mod. So here's your formula that you can use to solve quickly these things. And remember when we were solving those, how annoying it was? Let's take an example. 5x is congruent to 3 mod 11. So here's what we're going to do. First of all, 11 does not divide 5, and 11 is a prime. Therefore, we can say 5 to the 11 minus 2 times 5x is congruent to 5 to the 11 minus 2 times 3 mod 11. And then 5 to the 9, or this is going to be 5 to the 11 minus 1 times x is congruent to 5 to the 10 times 3 mod 11. What's 5 to the 11 minus 10 mod 11? What's that going to be? 5 to the 11 minus 1. 5 to the 10, but what is 5 to the 10 mod 11? 1 for Fermat's theorem. So this will be x is congruent to, and did I do something wrong? This should be 9, yeah. Thank you. This is 9. Can't subtract 2 from 11. Pretty sad. Pretty sad. So it's 5 to the 9. So you have 5 to the 9 times 3. mod 11. So now we just kind of go through it. I think you only do that once to get rid of that. Now we're going to have x is congruent to 5 squared to the 4th times 5 times 3 mod 11. And 15 is what, mod 11? 4. And 25 is what, mod 11? 22. 25 minus 22 is 3 to the 4th, mod 11. Almost there. 81. I would even go 3 squared. Mod 11, because that's negative 2. It'll work the same, won't it? So this is going to be negative 2 squared is negative 2 squared times 4 mod 11. And x is congruent to 4 times 4 is 16 mod 11. So I get x is congruent to 5. Is that the solution? Yep. And so back here, 25 minus 3 is what? 22 mod 11. So it works. So your answer for this is 5. Hold off on this theorem having to do with this. We'll come back to it. We're going to do a couple practice problems. So this is the end of video part 1, having to do with Fermat's theorem to simplify and solve equations.